welcome to this tutorial. In this tutorial we're going to see how we can simulate simple power electronic converters in this software known as the PSIM. So PSIM is actually a very easy software. You just need to, it's actually a plug and play software. You put the devices from different menus and put it in the model, and you connect them and you simulate them. So let us see how it works. So first of all, we need to have a blank project here. So this is we have made here. As you can see now, everything is enabled now. There are some commonly used power electronic devices on the bottom side, and there are some there's a menu box, drop box menu on the top slot. First of all, let me explain that this software is primarily made for the power electronic converters. Therefore, all the things that are available here are meant to be work in the industrial electronics or power electronics fashion. So first of all, let us see that for the elements, we have here a lot of elements ranging from the RLC branch, where you can find the resistor, the inductor, the capacitor, the RL series branch, RL parallel branch, and even the rheostat. We have also the saturable inductor, the coupled inductor, and nonlinear elements. Then we have here switches. In this menu on the switches, you can find all the power electronic switches available. It's not those on off manual switches. You can find here the diodes, the thyristors, the MOSFETs, IGBTs, and other power electronic switches. And then also, when we deal in the power electronics, we need transformers. So here a lot of transformers are available, including the 3-phase and the single phase with the inverted polarity, and the 3-winding and 4-winding and dual secondary. Same is here. We have magnetic elements available. In the other, you can find some control boxes that are op amp. For ground level, we have an optocoupler and other ICs. Then in this motor drive module, you can find the induction motors and other motors that can be used as a load, commonly used in power electronics. So here we have a magnetic coupler block. Then we have the permanent magnetic synchronous motor and other stuff. The most important and the interesting thing is this renewable energy block, where you can find the solar module that can be used for if you are working on a photovoltaic based system. Some boost converter, and you need a source as a photovoltaic. So there are two available. That is the solar module, which is a physical module, and the second one is a functional module. Now the basic difference, if you can just drag and drop them here, is that in a physical module you have to input the environmental conditions like the temperature and the irradiance. However, in a functional module of which is shown here, it actually works on the pretty standard testing conditions. That it assumes that you just put the open circuit voltage values and some brief values, and you get the result as a for the standard testing conditions of 1000 watt per meter square and at 25 degrees centigrade temperature. And then there is a wind turbine. Now in this control blocks, you can find filters, second order low pass filter, first order low pass filter. There are some computational blocks that includes the multiplier, divider, sine, R sine, and blah blah blah. And then there is a sample and hold switch lookup tables. You can have the FFT also available here. There is a total harmonic distortion calculator available. You can also have a S domain transfer function and S domain transfer function initial value. Another thing, in the logic elements, all the gates are available that are typically used in the logic section, AND gate, OR, NOR, and counters and other stuff. In this SIM coupler block, this is mostly not used in standalone application of the PSIM. The SIM coupler module is only used when you are having when you are having a co-simulation between two softwares. For example, if we will be seeing this thing in the later examples when we will be dealing the co-simulation, we will see an example of co-simulation from the PSIM and the MATLAB. So here in-link nodes actually have the data coming from the other software, and outlink nodes export the data of the PSIM to that other software. So it is not used if you are using a standalone application of the PSIM like we are using here. Then there are PI controller, proportional controller, and some other thing, comparator, and then saturation block like limiter. We can have a summer of with 3 inputs that can sum up to 3 inputs. And then we have some switch controller, PWM patterns, and in the sensors we can find the voltage sensor and the current sensors. Similarly, we can have a probe, DC voltmeter, and we can find the instantaneous power, the average power, the reactive power. We also have this oscilloscope available here. And then we have a function block, especially when we deal with the DQ control, or if we go for the vector control design of an induction motor drive. We need a lot of transformation from the ABC to DQ reference, and from the DQ to the ABC reference, and similarly alpha beta transformation. These are actually available here, and we also have some MATLAB function, math functions that have two inputs. They can you can apply different mathematical function on them. And then we have a control to power interface, AC sweep, parameter sweep, and other things. In the sources we can find these sources. Now you can see here the photovoltaic source is not available here. If you want to have a photovoltaic source or a wind turbine where you are having some sort of a renewable energy, it is not available here. It will be available in the power section here, as you can see here. So these sources also can have the DC, which is a simple cell, battery, sine wave, three-phase sine wave. We can have a triangular waveform, sawtooth, and other stuff, as you can see here. And then similarly we can have a current source as well, which could be a sine wave, DC, triangular, or other thing. Then we can have a constant, time, and some ground values. And then there is an even control and sim code for code generation. We are not going to deal with it. And the second thing is this simulation control. Now unlike the Simulink, in where we can just go into the into the dialog box, and we let me show you here, you can just go to the simulation, and then on configuration parameter, and you set some sample value here. We are not going to set a sample value here. However, we can put the sample in this simulation control. You put the simulation control here, and you double click here. It will ask you for the total time for the simulation, as well as the step size. So if you have a larger step size, you may get a waveform that has some sharp peaks, that is like a sine wave, which is not perfectly sine wave, but it has some sort of a peaky, some sort of like sharp peaks at its peak value. So let us see how we work. Now first of all is this: we need let us design a simple a simple diode rectifier, half wave rectifier. So you can see here we have a lot of things available. These are commonly used things, and most of the time you don't need to go into the elements to get the components. You find it here. So here in this section, you can see here this is a diode here. You just put it here, and if you right click on this diode, you can move the direction. So if I want to have it like this, just click it here, place it here, and then press the escape button. If you will not escape button, every click will make another diode available on your screen. And the second thing we need is we need a load resistor. So we can have a resistor here. We can just click on here to rotate its orientation. And the third thing is we need a voltage source. So now the voltage source is available here. You can see this is the sine wave, there is a DC voltage waveform, there is a triangular waveform, there is a square waveform, and then there is a step size step signal. So we are just using this sine wave here. Now to connect these four things with each other, we need to have a connection, and that is made, you can see on the upper side box, there is a wire written here. So if you just click here on this hollow button like this, and drag it, and it will eventually connect the circuit. The correct connection always has a red line with it. So if you are having some green line or only, it means there is something which is floating. And then you will connect this to the load, and then you connect it like here, and just connect a ground here, and you are finished. Now if you double click on this voltage source here, you can see the peak amplitude is 220. So let us have a 60 Hertz 110 volts system where our peak value is 169 volt, and let us change this frequency to 60 Hertz. And if we, since it's a diode, just increase this resistance, let us make it 50 ohm resistance. And we also need to measure some voltages. So for that, I mean, if you put a voltmeter here, you can have a voltmeter at this side here, and can have an ammeter in series here. So if you plot it here, and you have a voltmeter here, let us connect it here also, so that it is good to understand the things. Now you can double click here, and if you show probes value during simulation, if you click on this display, this value will appear after the simulation as I1, right? Because this is the first current sensor used in the circuit. and this should be V1, VP1, or we can call it voltage probe 1. We also need to display this one. And the second thing is this, I can also use this probe here. Now this probe is unlike the ammeter or a voltmeter. This probe can be simply used, and it actually measures this value with respect to the ground. We don't need to connect the second value. It just gives us the the voltage with respect to the ground. So let us call it VAC, and we want to display it as well. And let us see how our circuit will work. Now before that, I need to make it sure that the total time period is 0.1 second, and with 1 e raised to the power 0.05, let us make it 0.1 e raised to the minus 0.5. And if I play this, I have to click on this box. This is the run simulation box, and this is the run sum view where you will find those waveforms. So if I click it here, you can see the simulation has been perfectly simulated. We have a new dialog, we have a new window up here that has all the variables that we need to measure. The first one is the I1. Let us add this I1 here, and the second one is the VP1. We can have on the same window, but let us first plot only the I1. So this is the I1. As you can see, it's a diode, so it is rectifying this the AC voltage into a half wave. Now if you want to plot another curve on the same on the same window, you have to click here. This is add graph. So if you come here and you plot this VAC here, you can see this is the AC waveform. Now you can see, since this AC waveform has a peak of 169 and this is a 5, so we cannot it's difficult to zoom in here. So I will double click on here, I will remove this one, I will click here, and there is, you can see a lot of other mathematical operators here. So I will multiply it by, let us suppose I will multiply it by 50, and I will add it here. So now my current waveform is like this. And also if now this is in green color, because it actually, whenever you delete some graph and you plot again, it first comes, the first graph is in red, then in blue, then in green, and then in violet, and other type of color. So let us reduce this value a little bit, remove it here, and let us multiply it by 30 for example, and we will plot it, and you can see here. So this is the AC, this is the current, and you can see this gives us I1 into 30. The second thing is how I can plot a multiple, if I don't want to have it on the same graph, I have to click it here. Now if I click it here, I have this VPV1, I can plot it here. So this is my voltage waveform. Okay, and in here you can reset the you can reset this value here. See, sir? So if you have if you have just zoomed this section here, it will zoom all the way from above, because they have the same x-axis. So now if you want to reset this view, you can just redraw this value. And now if I want to have another, let us find the power. So it is the I1, I have to remove it. It is the I1 cross the VP1. It will give us the instantaneous power here, which is like this. And if you want to have an average value of this power, you can also have the average value of this power. You can just have this I1. You can see here there's an average. One is the moving average, another one is the periodic average. Let's have the moving average here, which actually is desired here. So the moving average of I1, and then we need a multiplier sign here. We'll put a multiplier sign here, and then this VP1, and then we need to close the brackets. So just and so this is actually this curly bracket here, and now the system is okay. Now you can see here, this is the average value, average power we will be getting out of this half wave single phase half bridge rectifier. So that is it, but I am more interested in telling you about this thing here. You can see here you can save this file, as you can print it. You can also have a measurement of minimum and maximum, and you can also perform the FFT as well. So now I have clicked this FFT, so it has given me some some components. You can find it here, the current wave FFT here. So you can see here we have some components of the DC value, and then we have on 60 Hertz we are having one component. Let me redraw this thing here, because this is a little bit interesting. So let us first delete the screen, and then another delete the screen. Let us remove this these two values, because I'm only interested in knowing the I1 here. So let us just add, just a minute, remove this one. I will just need the I1 here, and it has given me this whole value of FFT for the output current. So here we can see here, this is the output current in this section only, and this is where this is we can also set the x-axis as well. So if you don't want to have, so no, this is up to 2 kilohertz. Let us drag it to 1 kilohertz, and you can see here there we have a DC component. We have at 60 hertz. Then I think this is at the third harmonics. This is at the this is at around, I think this is the fifth harmonic, or there might be an interharmonics here. So this is how we can have it. We can also zoom in a little bit of area if you start playing with it, and you can also you can also have an x-axis instead of a frequency. You can have multiple, with respect to the, you can change the x-axis also. I'm sorry for this, but you can change the x-axis, and this is pretty important when we are dealing with the photovoltaic system, where we need to plot the photovoltaic curve and the IV curve. So that is it for the diode based rectifier. Now let us see what if we want to have a thyristor here, so that we could have some control on the angle. So for it, let us delete this one, and here you can see there is a thyristor available here. So if I click it here and we put it here, it is just as simple. I have just replaced this diode with this, and before that let me have this thing here, so that I'm more interested in getting to know what is the AC current here. Now we have to turn this on. This turning on means that this has to be turned on at specified interval if you want to get some output across the load. So for this, there is, you can see here, there is one block available here. This is the gating block for the switches. Now if I just click it here, you see it is available here. And sometimes with some circuits, this line is green line. If you are having that green line, just place this on-off switch controller in between this gating signal and the device, and it will work fine. So if I double click here, you can see here here is the frequency. Now since it's a thyristor, I'm not having this gating signal with the MOSFET, so this should work with the line frequency. So let us first convert this into 60 hertz signal, and then we have number of 2 points. I just need to turn it on. Now my first, if I turn on the switch for a small interval of time, it will turn on as long as we have a positive half cycle on the anode of this thyristor. So this means that we are not forcing it to commute. It will naturally commute. So a very small pulse is required. So if I just put this 0 here, and a small pulse mean, let us put a 5-degree pulse here, it will give us exactly the same value as the diode. Let us see how. Now if I click it here, we just need to know the VP1, the load value. What you can see here, this is exactly what was produced by a rectifier, which was an uncontrolled one. And if I put this VAC here, you can see this waveform and this waveforms are of same value. Why? Because at exactly 0 degree you are firing it. Now let us suppose that we want to have a 45-degree phase difference, a firing angle of 45 degrees, so that the device will conduct after the 45 degree of each positive half cycle, and only for the positive half cycle, because this is a half bridge rectifier. So what I will do is this, I will put it 45 and make it 50. So just this, even if I make it 47, this 2 degree pulse is enough to turn on this switch perfectly. Now if I turn this on, you will see that the VP1 will not be exactly the one we have seen for the diode based rectifier. So you can see here there is a delay of 45 degree. Okay, now if I want to have a delay of, if we want to have a delay on even more, we can have it, for example 80, make it 85, and you can see here it will only it will clip a majority of the input waveform and will give us a value which is like this. So that is how you can control the firing angle of a thyristor here. So this is all for this tutorial. I hope you enjoy it, and stay in touch, stay glued with my channel. Inshallah, we will be having we will be discussing how we can use a photovoltaic modeling in the next class. Thank you very much.